The evolution of transport technology overview. Transport technology has evolved from simple copper wires to sophisticated all-optical networks. Technology era. Primary characteristic PDH, plesiochronous digital. Early digital system, rigid and difficult to manage at 1970s to 80s. Hierarchy, scale. SDH/SONET, synchronous. Introduced synchronization, allowed for better 1990s digital hierarchy, management and protection, rerouting. WDM/DWDM, wavelength 2000s allowed multiple colors of light on one fiber, division multiplexing, present multiplying capacity by 100x or more. Often called the digital wrapper, it combines the OTN, optical transport current benefits of SDH, management, with the speed of network, WDM. PTN/MPLSTP, packet optimized for packet traffic, internet data, rather current transport network, than old-fashioned constant voice streams. Core components. A transport network isn't just cables, it's a complex system of hardware and software. 1. Physical media, primarily fiber optic cables, though high-capacity microwave links are used in areas where laying fiber is impossible. 2. Transponders/muxponders, devices that convert electrical signals from routers into optical signals, light, to be sent over the fiber. 3. ROADM, reconfigurable optical add-drop multiplexers, the traffic lights of the optical world, allowing operators to change the path of a specific wavelength of light remotely without manual intervention. 4. Control plane, the brain, increasingly driven by software-defined networking or SDN, that monitors network health and manages traffic flow. Modern trends, 2025 to 2026. As we move further into 2026, the transport network is undergoing 3 major shifts. 400G/800G and beyond, networks are upgrading to 400 Gbps and 800 Gbps per wavelength to handle the explosion of AI-generated content and 5G/6G data. Autonomous networking, using AI to predict failures before they happen and optimize power consumption. Quantum-safe encryption, implementing new security protocols in the transport layer to protect data against future quantum computer threats. 7. The evolution of transport networks is the history of how the pipes of the internet grew from carrying simple voice calls to supporting massive AI workloads. This journey has moved through 4 distinct eras, driven by the need for higher capacity, better management, and lower latency. The early digital era, PDH, 1960s to 1980s, before fiber optics became standard, the plesiochronous digital hierarchy, PDH, was the first major step into digital transport. The technology, PDH, used time division multiplexing, TDM, to combine multiple voice channels into a single high-speed line. The problem, plesiochronous means nearly synchronous. Because different parts of the network weren't perfectly in sync, it was impossible to extract a single 2 Mbps signal from a 140 Mbps stream without demultiplexing the entire stack, a process known as the multiplexing mountain. Standardization, it lacked a global standard, with different systems used in North America, Europe, and Japan. The golden age of voice, SDH/SONET, 1990s, as fiber optics emerged, the industry needed a more organized way to manage traffic. Synchronous digital hierarchy, SDH, and SONET in North America, solved the synchronization issues of PDH. The innovation, everything was perfectly synchronized to a master clock. This allowed for add-drop multiplexing, ADM, where you could pull out a specific data stream at any point without disturbing the rest of the traffic. Reliability, it introduced self-healing rings. If a fiber was cut, the network could reroute traffic in less than 50 milliseconds, a gold standard still used today. Limits, SDH was built for voice, fixed 64 kilobytes per second circuits. As the internet grew, its rigid structure couldn't handle the bursty nature of data traffic efficiently. The capacity explosion, WDM and OTN, 2000s to 2010s, to meet the bandwidth hunger of the internet, carriers stopped trying to make faster single signals and instead started sending multiple signals at once. WDM, wavelength division multiplexing, instead of one light signal per fiber, WDM sends many colors, wavelengths, of light down one strand, instantly multiplying capacity. OTN, optical transport network known as the digital wrapper, OTN combined the massive capacity of WDM with the management features of SDH. It allowed for the transport of any service, Ethernet, storage, video, inside a standardized frame. Capacity, this era saw the jump from 10G to 100G and eventually 400G per wavelength. The modern frontier, 800G, FGOTN, and AI, 2020s, present, as of 2026, the transport network is no longer just a passive pipe, it is becoming an intelligent, AI-native fabric. 800G and 1.2T, modern networks are deploying 800 Gbps and 1.2 Tbps per wavelength to support data center interconnects, DCI, and AI training clusters. FGOTN, fine-grain OTN. This is the newest evolution, designed to bridge the gap between old SDH systems and new high-speed pipes. It allows for tiny hard pipes, as small as 10 Mbps, to be carried securely within 100G/400G networks critical for power grids and industrial automation. Autonomous networks. Networks are now self-healing using AI agents that predict fiber breaks or signal degradation before they happen. Summary table error key technology main driver primary unit 1970s PDH digital voice 2 Mbps, E1/1.5 Mbps, T1, 1990s SDH/SONET global interop/reliability 155 Mbps, STM1, to 10 Gbps 2010s WDM/OTN internet/video growth 100G/400G wavelengths 2025 plus 800G/FGOTN/AII/IoT/cloud 800G plus and multi-granularity. In the transition to 5G, the transport network stopped being a single linear backhaul pipe and evolved into a complex, multi-layered architecture known as X-Haul. To manage this complexity, the industry moved away from manual configuration toward SDN, software-defined networking, automation. 5G X-Haul, the three-layer architecture. Traditional 4G networks mostly relied on backhaul, connecting the cell site to the core. 5G disaggregates the base station into three parts: the RU, radio unit, DU, distributed unit, and CU, centralized unit. This created three transport segments: front haul, RU to do the most demanding layer. It requires ultra-low latency, often 150 Us, to handle raw radio signals. It has moved from proprietary CPRI protocols to eCPRI, Ethernet-based, allowing it to run over standard fiber networks. Mid-haul, due to CU connects the distributed processing units. It is less latency sensitive than front haul but requires high throughput to aggregate data from multiple towers. Backhaul, CU to core, the final stretch that connects the mobile network to the 5G core. This is typically high-capacity IP/optical transport. SDN automation, the brain of the network as of 2026, managing these thousands of X-Haul segments manually is impossible. SDN decouples the brain, control plane, from the muscle, data plane/hardware. Centralized orchestration, instead of logging into every router, engineers use an SDN controller to program the entire network. If a 4K video stream requires more bandwidth, the SDN controller automatically adjusts the path segment routing, SRv6. This is the GPS for 5G packets. SDN uses segment routing to tell each packet exactly which path to take through the network to meet specific latency or security requirements. Zero-touch provisioning, ZTP. When a new 5G small cell is plugged in, SDN automation detects it, configures the X-Haul parameters, and brings it online without human intervention. The killer app, network slicing. The combination of X-Haul and SDN enables network slicing, the ability to run multiple virtual networks on one physical fiber. Primary slice type. How SDN/X-Haul delivers it. Requirement: autonomous routes traffic through the shortest front haul path, ultra-low latency driving with high priority. High connection uses low bandwidth mid-haul paths to save massive IoT density, energy and costs. Mobile dynamically allocates 400G 800G backhaul, massive throughput broadband capacity during peak hours. What's happening in 2026? We are now seeing the rise of AI-driven SDN, where the controller doesn't just follow if/then rules but uses machine learning to predict congestion and reroute X-Haul traffic before a slowdown occurs.